Okay, so this is the second video about fraction multiplication, but I want to sort of go over something really quick. And it's this idea of the fraction bar itself being a division symbol. So what I mean is if you have something like 6 over 3, this is really saying, so right, it is a fraction. It's saying 6 thirds, right? But it's also saying 6 divided by 3. So you can read the fraction bar as, like, when you see it, you can read it in your head as saying divided by, so if you have some numerator, it's being divided by a denominator. So it's not that the other way I talked about it is not valid, right? When remember when I talked about, so if I had something like 1/3, I said you have, something is broken into thirds. The denominator tells you how many pieces it's broken into, and then the numerator tells you how many of those pieces you have. These are both valid ways of thinking about this. Sometimes it's better to think about it, in terms of just division. Sometimes it's better to think about it in terms of like parts of a whole. It depends on the problem you're doing, but either way, it works. And that's how you'll find a lot of math is. And maybe that's why math is so frustrating to people sometimes, is because no one ever tells them that. Like, there is no one way to look at something. There's plenty of ways to look at something, and some ways are more helpful than others in certain situations. So I want to introduce you to both ways so that you can apply either way of thinking to a specific problem and see if it makes it easier for you to solve it. So yes, so 6 over 3 or 6 thirds also means 6 divided by 3. And 6 divided by 3 is 2, right? So we say 6, let me rewrite that, 6 there. 6 over 3 is equal to 2, right? Because we know that. We know if you did the old-fashioned way, right, of writing this would be like 6 divided by 3, right? And you say, oh, it goes up 2 like that. You multiply the 2 and the 3, you get minus 6, you get a remainder of 0. And like, okay, yeah, it equals 2. Another way, you can say this is 6 divided by 3 equals 2. And this, both of these are, valid ways of doing it. But I will say, as you move up through math, through like I think pre-algebra is when you stop seeing this symbol. Maybe algebra, but we don't really use this symbol anymore because it might not appear to be this way right now, but it's kind of ambiguous if you were to write out like a string of operations and you don't know which ones are being divided by what. So we actually write things with fraction bars, which make it much more clear as to what's being divided by what. So anyways, if that doesn't make sense, don't worry. It'll make sense to you down the road the more you move through algebra and you get into more complex problems. Okay, so that's what that means. And another thing, so it means it's a division symbol, it means divided by. Another thing I want to talk about is reducing fractions. So one thing you could have thought about when we had this 6 over 3 and then we said it equaled 2 is we reduced the fraction down. We made something that was a fraction into something simpler. And actually, this could have been 6 over 3 could have been rewritten as 2 over 1. And 2 over 1 is a fraction, and 2 over 1 is equal to 2. So that actually brings up another good point, is that any whole number, 1, 2, 3, 4, 5, any of those numbers, they are also fractions because you can rewrite them as being divided by 1. Because what does that mean if something's divided by 1? It doesn't change the value, right? Like 6 divided by 1 is still 6. So they're the same thing. They're interchangeable. You could write them either or. Okay, so just in case that's confusing, I wanted to go over that in case it was confusing why that would be over, 2 over 1 is equal to 2, and it's the same, literally the same thing. So, but I want to talk about this idea of reducing fractions. So what if we had it the other way around? What if it wasn't 6 over 3, but 3 over 6? Well, we could think of this as being 1/2 pretty easily without even knowing about reducing. And we would think that because we say, well, we know that 3 is half of 6. So therefore, it has to be 1/2. But mathematically, what are you doing to do that? Like not just like knowing this intuitively, but how is a way you can show that this really is 1/2 mathematically? You can look at the numerator and the denominator and ask, do these things share a common factor? What I mean by factor is a number that divides into them evenly. So when I say evenly, I mean without a remainder, right? And if they do share a common factor, you can think of dividing both of those numbers by that factor to make them smaller. So here we could see that 3 and 6 have a common factor of 3. And yes, a number is a factor of itself. So 3 is a factor of 3. 3 is also a factor of 6. So we can think of, and usually we cross them out like this. We say, if 3 were divided by 3, it would equal 1. And if 6 were divided by 3, it would equal 2. And then we see, oh, well, then we're left with 1 over 2, right? 1/2. So that's how fraction reduction works. So let's do another one to see how this, to make it more clear. What if we have 5 over 25? Well, do they share a common factor? Yes, 5 is a common factor of both. So we want to cross them out to reduce it, right? So we say, okay, the numerator, if we divide 5 by the common factor, 5, we get 1. If we divide 25 by the common factor, 5, we get 5. And this whole thing simplifies to 1/5. So let's try one more, just one more, and then I'll go on to another example to show why this really works. So what if we had 14 over 21? Do these share a common factor? I hope, and usually what I do, if I don't know, I kind of run through the numbers. So I go, and I never consider 1 because 1 is common to all numbers, but I would look at 2 and I would say, okay, 2 goes into 14, right? Does it go into 21? No. Then I would try 3 and I'm like, oh, 3 goes into 21, but it's going to 14. I'd run through all this until I finally arrived at 7, and I'd say, oh, 7 goes into 14 and it goes into 21. So I can reduce by effectively dividing both numerator and denominator by 7. So I can go, okay, 7 goes into 14 twice, and it goes into 21 3 times, and so this ends up being 2/3. So 14/21 or 14/21 simplifies to 2/3. It is 2/3 essentially. It's a bigger way of reporting it, but if you were to simplify it down, reduce it down, it is 2/3. Now you might be asking, like, why is that working? Is this some sort of magic, some trickery? And no, it's not. So let's look at an easy one to prove the point. So if we had 2/4, okay, well, let's look at this geometrically. I think if you're ever unsure, try to draw something geometrically if you can, because it makes it a lot more real to us when we can see something like that. So what I mean geometrically is like, let's draw a shape, like a square. And let's think of that square being cut into 4ths, right? And we have how many of those 4ths? We have 2 of them. So that's like, if we were to shade in one of these right here and shade in this one here, right? We shade in 2 of the 4 4ths. And then how much of the overall square, because all we really care about is how much of the overall square is shaded in. Well, yeah, 2/4. Or you could think about it as, oh, this whole entire left half is shaded in. So we could do what I showed you here, how to reduce, right? And we would get 1/2 because we say, well, 2 goes into 2 once, 2 goes into 4 twice, and this equals 1/2. But here I'm showing you with the real square that, yeah, it is 1/2. And that's what you're doing when you're reducing. So this thing with this up here, this 5/25, if I could actually, nicely draw a square that was broken up evenly into 25 individual parts, and I shaded in 5 of those squares, the little squares inside the bigger one, and then we would see that this could be thought of as overall 1/5 of the total. But I can't do that because I'm not an artist, and it would take a long time. It probably would look terrible if I tried. So, but the point is that when you're reducing, you're not actually changing the value of anything. You're just reducing it into a simpler way of reporting it. saying we have 1/2 of the square is a simpler way of saying we have 2/4 of the square, right? So, okay. Now that hopefully this whole idea of reduction of fractions hopefully makes sense now, I want to talk about canceling, or cross-canceling rather, of fractions. So this goes back into the multiplying two fractions. So let's look at another example real quick. What if we had 1/4 being multiplied by 2/3? Well, if you remember from the last video, I said that's the way you do this. Is you take the two numerators, you multiply them. Take the two denominators, you multiply them. That would be 4 times 3, right? And then you'd end up with 2/12. But then we can reduce this 2/12 because we know that 2 goes into 2 and 2 also goes into 12. And this is, by the way, always check when you get some answer. You need to always check, is this thing able to be reduced? If it is, reduce it, because that's the proper answer. We want things in their simplest form possible. So if you're in a class right now and you are working on these types of problems like adding or multiplying fractions and you don't reduce, you actually will get marked wrong. So I'm trying to warn you right now, is always check if they can be reduced. And can 2/12 be reduced? Yes. 2 goes into 2 once, 2 goes into 12 6 times, and so we get that 2/12 is equal to 1/6. But you know what? We could have taken care of this beforehand, before we ever got to this point. And the way we could have taken care of it is by this method called cross-cancellation. And so we could have gone, I'm going to go back to this point where we had the beginning where you had 1/4 times 2/3. And what you do here is you look at the numerator of one fraction and the denominator of the other fraction and see if those two things are, if they share a common factor. And if they do, you can cancel them out. The way we do it up here when we reduce a single fraction, you do the same thing. You say, okay, let's look at 1 and 3. Do they share a common factor? Only 1, and that we don't care about that. So forget about 1s. 1 and 3 do not have any other common factors. What about 2 and 4? 2 goes into both, right? 2 goes into itself once. 2 goes into 4 twice. And then if we do this, we get 1 times 1 over 2 times 3. And guess what? We still get the 1/6 that we got up here, except with one less step to get there because we didn't have to reduce at the end. We took care of that by cross-canceling. And so cross-canceling is a very powerful method, and it works. The power of it becomes more evident when you are doing bigger fractions. So these are small fractions, so it might not seem like it's very useful necessarily, but let me show you when it is really useful. So what if I had 5 over, let's see here, 5 over 21 and then be multiplied by 14 over 25. How about that? Okay, well, if I didn't try to cross-cancel, let's see what we would get. On top, we'd have 5 times 14. And on bottom, we have 21 times 25. And then, okay, if I asked you what 5 times 14 is, we have a lot of our times tables memorized, but you probably don't have 5 times 14 memorized. It wouldn't take you too long to figure it out, right? You'd have to go maybe off to the side, or you could do it in your head maybe and do this, 5 times 14, but that's a lot of work, more work than we care to do, especially when we're on a test and we need to go quickly, right? Same thing with 21 over 25. That's, you're most likely going to have to go and do that on paper, like off to the side. And then what's going to happen is you're going to end up with some big number, right? Some big number divided by some other big number. And you need to know, can this reduce, right? Can it be reduced? I don't know. It's going to be harder to find a common factor between two really big numbers. So now maybe not these because they both end in 5, but that doesn't matter. But usually it's pretty hard to know whether or not you can reduce that if it's a really big number. So why not deal with the reduction part from the very beginning? So we never do 21 times 25 or 5 times 14 because we take care of this right at the very beginning by looking at this numerator, the 5, and this denominator, 25, and we say, hey, those have a common factor of 5. And so we can cross cancel. Cross comes from, you're going numerator and denominator this way, so that's why it's called cross, like that. So here we can say this 5 goes into itself once, and it goes into 25 5 times. Already this numerator went from a 25 to a 5. A lot smaller, right? What about these ones? Do these cross cancel at all? Because they don't have to, right? You can cross cancel just one way. You don't have to do it both ways, but if you can, that's even better. 14 and 21, yeah, they share a common factor of 7. 7 goes into 14 twice. 7 goes into 21 3 times. So now we just took these really big fractions and we said, oh, this is like as if we were just saying 1/3 times, right? Because that's 1, and then that simplified to 3 times 2/5. Oh, that just ends up being 2 over 15. That's a lot easier than going through all the other steps we would have had to do. So that is the power of cross-cancellation. And cross-cancellation, by the way, only works for multiplication and division of fractions, but we'll cover that later. It's the reason why it works for division is because division of fractions, as it turns out, is really just a different way of multiplying, which we'll see. So for right now, I just want you to see to kind of make a mental note that only works for multiplication. So don't even try doing this with addition or subtraction because it doesn't work, and you'll get the wrong answer if you do that. So okay, I guess that's a good place to stop for this video, and the next video cover fraction division.